Welcome to the Deep Dive. Today, we're really getting into the heart of modern aircraft, the electrical systems. If you're working through your AMT airframe material, this is Chapter 9. Essential stuff.
Absolutely essential. The reliability of these systems isn't just important, it's critical. Our sources are crystal clear on this. One mistake during maintenance, one careless installation.
And you've got an immediate hazard. We're talking smoke, fire. It's serious business.
Exactly, which is why we always start with the basics, Ohm's law.
Right. E equals I times R. Voltage equals current times resistance.
And you really need to grasp this, not just memorize it. For troubleshooting, it's everything. Why does a breaker pop?
High current, obviously. But that's the symptom, isn't it?
Precisely. The cause is usually the resistance dropping. Think about a short circuit. Resistance R goes way down, maybe close to zero.
And if the voltage E stays constant, which it does in parallel circuits,
then I, the current, has to shoot up massively. And that sudden spike, that's what generates dangerous heat. P equals I squared R. That heat trips the breaker, hopefully, or it starts melting things.
And remembering that most aircraft loads are wired in parallel is key. That voltage is always there, ready.
Ready to feed that fault? Yep.
Okay, let's break down the players here. Current I, measured in amperes. What's an ampere, really?
Well, technically, it's the international unit. It represents 1 coulomb of charge moving past a point in 1 second.
And a coulomb is a lot of electrons.
A staggering number, like 6.28 times 10 to the 18th electrons, almost impossible to picture.
So maybe think of it like electron traffic. Gallons per minute, but for electricity.
That's a decent analogy, and if current is the flow, the traffic, then voltage, E, or electromotive force, EMF, that's the push. It's the electrical pressure, measured as a difference between 2 points.
Like the 12 or 24 volts across a battery.
Exactly. It's always a potential difference. The water tank analogy really helps here, I think.
Oh yeah, figure 9 to 4 in the texts. Explain that one.
Okay, so you have two tanks, A and B. Tank A has 10 psi, tank B has 2 psi. Water flows from A to B, right?
Sure.
But not just because A has pressure, it flows because there's an 8 psi difference between them.
Ah, okay. The difference drives the flow.
Precisely. Same with electrons. They move from the negative terminal, think of it as high pressure, an excess of electrons, to the positive terminal, the low pressure area, a deficiency. It's all about that potential difference.
Which brings us to that classic point of confusion for students.
Yeah.
Which way does the current actually flow?
Right. The two theories. Conventional flow, positive to negative, which is the older idea, and then electron theory, negative to positive, which reflects the actual movement of electrons.
And the FAA standard.
Electron theory, negative to positive. That's the one you need to know for your exams and documentation. Honestly, in the field, as long as you're consistent with whichever theory you use for tracing a circuit, you'll likely find the fault. But for standardization, stick with electron theory.
Okay, good clarification. So, we understand the flow. How do we generate this power on board? I know there are a few ways, like solar or chemical.
True, but for primary aircraft power, it's almost universally electromagnetic induction, generators and alternators.
The basic principle being?
Move a wire or a conductor through a magnetic field, and you induce a voltage in that wire. Simple as that.
Yeah.
Now, how much voltage you get depends on things like how many turns of wire you have in your coil and how strong that magnetic field is.
And we have two main types doing this. DC generators and DC alternators. What's the key difference?
It really comes down to how they turn the AC they inherently produce into the DC the aircraft system mostly uses. A DC generator makes AC internally in the armature windings. Then it uses this mechanical rotating switch called a commutator with brushes riding on it to kind of flip the connections externally and deliver pulsating DC.
Okay, sounds like a lot of moving parts.
It is, and high maintenance. Now, the DC alternator also makes AC internally. Usually 3-phase AC, which is smoother. But instead of commutator, it uses a solid-state rectifier assembly, usually 6 diodes. These electronically convert the AC to much smoother DC. No sparking, no mechanical switching of the main output current.
And that difference in construction leads to a big maintenance advantage for the alternator, right?
Huge advantage. Think about the brushes. In a DC generator, the main output current, which can be really high, flows through the brushes and commutator segments. Lots of wear, lots of earthing.
A maintenance item.
Definitely. But in an alternator, the brushes only carry the low current needed to energize the rotating magnetic field, the field current. They ride on smooth slip rings, not segmented commutators.
So less current, less wear, much longer life.
Exactly. Smaller brushes, less maintenance needed. big win for reliability.
But both types need control because the engine speed driving them changes all the time.
Right. You need a stable voltage, like 28 volts DC. Regardless of whether the engine is idling or at takeoff power, that's the job of the generator control unit, or GCU, sometimes called a voltage regulator. And how does it control the voltage? By managing the strength of the magnetic field.
How?
It adjusts the amount of that small field current we just talked about. Less field current means a weaker magnetic field, which means less induced voltage. More field current, stronger field, more voltage.
And the GCU does this automatically. I remember the older types, the vibrating relays and carbon pile regulators.
Yeah, those are electromechanical nightmares sometimes, always needing adjustment, sensitive to vibration. Modern systems use solid-state regulators. Much more reliable. They use transistors and often a Zener diode as a super stable voltage reference. The circuitry compares the generator output voltage to the Zener reference and adjusts the field current through the transistors. Much faster, much more accurate, way less maintenance.
Makes sense. Now, shifting gears a bit, larger aircraft often use AC power extensively. Let's talk about AC values. There's instantaneous, peak, but what's the one we usually see on ratings?
That would be the effective value, or RMS, root mean square.
RMS. Why is that the important one?
Because it gives you the equivalent heating effect compared to DC. So if a resistor produces a certain amount of heat with 10 amps DC, the RMS value of AC that produces the same amount of heat in that resistor is 10 amps AC RMS. When you see a system rated for, say, 115 volts AC, that's the RMS value. It's the practical, usable measure.
Okay. And AC circuits are more complex than DC because current faces more than just simple resistance.
That's right. In DC, you only worry about resistance. R, it opposes current, creates heat. Simple. In AC, you have three types of opposition.
Sure.
First is still resistance. Behaves pretty much the same, causes heat, no weird phase shifts.
Okay.
Second, you have inductive reactance, XL. This comes from inductors' coils of wire, like in motors or transformers. As the AC cycles, the changing magnetic field in the coil creates a countervoltage that opposes the change in current.
So it resists the flow.
It opposes the change in flow, yeah. And this opposition, XL, depends on the frequency F of the AC and the inductance L of the coil. The formula is XXLA equals 2 pi FLA. The really key thing to remember about inductors in AC is they cause the voltage to lead the current. Think ELI, the IC man, E before I, NL. Okay, voltage leads current in an inductor. And the third, opposition.
That's capacitive reactance, XC. This comes from capacitors. They oppose the flow of current by storing and releasing charge. This opposition, XC, is inversely proportional to frequency F and capacitance. So dexcelery equals 1 to L of C. Higher frequency or bigger capacitor means less opposition.
And its effect on phase?
It does the opposite of an inductor. Capacitors cause the current to lead the voltage. That's the ICE part of ELI, the Iceman at I before E and C.
ELI.
Yes, E-man, got it. So in a real aircraft circuit with motors, lights, capacitors, all three oppositions are present. How do we calculate the total opposition?
That total opposition in an AC circuit is called impedance, symbolized by Z.
And you can't just add R, XL, and XC together, can you?
Absolutely not. That's a classic mistake. Because inductive reactance and capacitive reactance act 180 degrees out of phase with each other, they effectively cancel each other out to some extent, and both reactances are 90 degrees out of phase with resistance.
Sounds like vector math.
It is exactly vector math. Think of resistance as a horizontal force, and the net reactance, XL minus C, as a vertical force. Impedance, Z, is the hypotenuse of that right triangle. So you use the Pythagorean theorem, Z is equals core 2R2 plus XLXC2. The takeaway is impedance is the overall opposition, and you need vector math, not simple addition, to figure it out. It's crucial for sizing components and protection correctly.
Okay, impedance. Makes sense. Let's move to stored energy batteries. What are the main types we see?
Primarily, you'll see flooded lead-acid batteries, especially in smaller general aviation aircraft. And then nickel-cadmium or 9-steed batteries are very common in corporate and commercial jets. There are also newer sealed types like valve-regulated lead-acid, VRLA.
And their functions, starting, backup.
All of the above. Ground power for starting engines or APUs, critical emergency power if the generators fail, and also acting like a buffer to stabilize the DC bus voltage during high-demand spikes.
Capacity is rated in ampere hours. Ugh. What affects that capacity in real life?
Two big things, discharge rate and temperature. If you discharge a battery really fast, its effective capacity is lower than the rating. But temperature's huge. They like it moderate, say 60 to 90 degrees Fahrenheit. Too cold, the chemical reaction slows way down, less power available. Too hot, and you shorten the battery's life significantly, risk thermal runaways and nucleates.
Okay, now, the big safety warning.
Okay.
Servicing different battery types.
This cannot be stressed enough. Never ever service or store flooded lead-acid batteries and NiSid batteries in the same room or use the same tools without meticulous cleaning.
Why is that so critical?
It's chemical warfare at the electrolyte level. Lead acid uses sulfuric acid electrolyte. NiSid uses a potassium hydroxide solution, which is alkaline base. If even a tiny amount of acid gets into the alkaline electrolyte of a NiSid, or vice versa, it causes permanent, irreversible contamination and destruction of the battery cell. You cannot fix it.
Total loss.
Total loss. The only exception is sealed VRLA batteries. Because their electrolyte is absorbed or gelled and they don't spill, they can generally be serviced in the same area as NiSids, but you still need care. Always check the manufacturer's maintenance manual.
Good warning. And for those flooded lead-acid types, they need regular checks, right? Water levels.
Yes. During charging, they produce hydrogen and oxygen gassing, which consumes water from the electrolyte. So you need to periodically check and top up with distilled water. And crucially, you need to check the specific gravity of the electrolyte with a hydrometer.
Why is that important?
Specific gravity tells you the state of charge. A fully charged battery has denser electrolyte, maybe 1.275 to 1.300 reading. A discharged battery has electrolyte that's much closer to plain water.
And plain water freezes easily.
Exactly. A discharged lead-acid battery can freeze solid in cold weather, which can crack the case or damage the internal plates. So monitoring specific gravity, sometimes correcting the reading for temperature, is vital for battery health and preventing freeze damage.
All right, let's talk about wiring itself. Installation, protection. Modern standards like MIL-W 22759 are pretty strict.
They have to be. We differentiate between a wire, a single conductor, maybe stranded, with insulation, and a cable, which is two or more conductors bundled together, maybe shielded or twisted.
And choosing the right size wire, the gauge, is critical. What factors go into that decision?
Several things. First, it needs enough mechanical strength to not break from vibration or handling. Second, you want to minimize power loss due to the wire's own resistance, that's I to $1 loss, which shows up as heat.
Heat again, the enemy.
Always. And third, you need to control voltage drop. You don't want the voltage at the equipment to be significantly lower than the source voltage. Typically, you aim for less than, say, a 2-volt drop in a 28-volt system for continuous operation loads. And remember, the AWG scale American wire gauge is kind of backwards. Smaller numbers mean larger diameter wires. #10 wire is much bigger than a #20 wire. You generally pick the largest size practical for the current load to minimize resistance and heat.
Okay, wire sizing. Now, routing. There are some really strict rules about keeping wires away from fluid lines.
Non-negotiable safety rules. Wires must be kept physically separate from lines carrying flammable fluids, fuel, oil, hydraulic fluid, or oxygen. The minimum separation whenever possible is 6 inches.
6 inches? Why so much?
Think about a pinhole leak in a pressurized hydraulic line. That fluid can spray or mist quite a distance. 6 inches provides a buffer to prevent that fluid from soaking into the wire bundle insulation, which could lead to degradation, short circuits, or fire.
And if you can't get 6 inches?
If routing absolutely requires them to run closer, say parallel in a crowded wing route, you need at least 2 inches of separation, and they must be securely clamped so they can't shift closer.
Got it. And the drip loop.
Ah, the drip loop. Simple but effective. Whenever wires enter a junction box, connector, or piece of equipment from above or horizontally, you route the wire so it goes slightly below the entry point and then loops up into it.
So gravity helps.
Exactly. Any condensation or fluid that might run down the outside of the wire will follow the loop down and drip off at the bottom instead of wicking straight into the electrical connection. Prevents corrosion and shorts.
Smart. Finally, protecting the circuits themselves. Fuses and circuit breakers.
The two main types. Fuses are simpler. Basically, a strip of metal designed to melt and break the circuit if the current gets too high. You have fast-acting and slow-blow types, depending on the application. But once they blow, they must be replaced.
And circuit breakers.
They're reusable switches that automatically trip open when overloaded. Critically, aircraft circuit breakers must be trip-free. That means you cannot physically hold the button or toggle in to keep the circuit closed if there's an actual fault causing it to trip.
Important safety feature? And the procedure if one trips.
The rule is generally, if a breaker trips in flight or on the ground, and there's no obvious associated smoke, smell, or system failure, you can reset it once.
Just once.
Just once. If it trips again immediately or after a short time, do not reset it again. There's a definite fault in that circuit that needs to be found and fixed through troubleshooting. Don't just keep pushing it.
Okay, we've covered a lot of ground here. From the absolute basics of Ohm's law at electron flow, through generators versus alternators, AC impedance, battery safety, and right down to how you physically install and protect the wiring.
It really shows how interconnected it all is. And when you think about the complexity moving up to larger multi-engine aircraft, well, the control systems become incredibly sophisticated. We talked about individual GCUs managing voltage or frequency, but making multiple generators or alternators work together in parallel, that's a whole other level.
Paralleling generator.
Yeah. For DC generators, they need load balancing circuits to share the load evenly. For AC alternators, it's even tougher. They need to be perfectly synchronized in voltage, frequency, and phase angle before they can be connected to the same bus. That often requires things like constant speed drives, CSDs, or integrated drive generators, IDGs, to keep the alternators spinning at the exact right speed for 400 Hertz, regardless of engine RPM. And then complex computerized controllers like bus power control units, BPCUs, manage the paralleling and protection. It's really the seamless integration of these systems that ensures overall reliability and safety.
That complexity really underscores the need for solid foundational knowledge. All right, to wrap things up, here's something for you listeners to think about. The hot battery bus. We mentioned batteries provide emergency power. The hot battery bus takes that a step further. It's wired directly to the battery. Always live, even if the main battery switch is off. So consider the implications. What systems are so absolutely critical that they need power available instantly, even in a complete electrical failure scenario, drawing directly from the battery? Think about that responsibility. Things like fire extinguisher circuits, maybe fuel shutoff valves, the aircraft clock. It really highlights the safety philosophy built into these electrical designs. Thanks for joining us on The Deep Dive.